In this video I want to talk again about the so-called relaxation oscillator or the blocking oscillator. There was an earlier video and I want to give the link in the description, the text box. I was talking in the earlier video about the Ferrite transformer, but now in this case I have used a standard 50 Hertz transformer that was originally made to generate these voltages. So 12 volt at 0.75 watt, two windings of them, and on the secondary 230 volts. So here you see the secondary. Perhaps it's important to tell that. Here you see that secondary. It has a certain ohms resistance, but of course when such a transformer oscillates on 50 Hertz or 60 Hertz, the AC resistance differs from the ohms resistance, the DC ohms resistance, etc., etc. So this is all what I wanted to point it out. I've used these two, say, 12 volt outputs at 0.75 watt to be driven with the Darlington of 2BD139 transistors. And because it is a transformer that is originally made for 50 Hertz, the frequency where it all works drops down to a lower value, say in the range of 100 Hertz up to approximately 800 Hertz. Has also to do with the backcoupling capacitor here. So let me show the schematic. So a few changes. So in this video regarding the blocking oscillator, so it's part 2 now. This is the schematic. In fact, everything is the same compared to the earlier schematic. No real changes are made. But here you see the transformer, the reversed, say, wall transformer with two separate 12 volt windings, by the way. The DC resistance of the AB winding is 70 ohms, the D winding is 70 ohms, and the high voltage winding, because it is a reversed transformer, is 3500 ohms, 3K5. So such a normal transformer for 230 volts at 50 Hertz can be used as a high voltage transformer when you reverse the winding and send in to the primary windings a substantial amount of voltage and current. And that's done here. To make it work on a lower frequency, the high voltage circuits make to work on a lower frequency. Of course, I had to adapt this capacitor to a higher value where that worked properly. So it's now 0.47 microfarad, that is 470 nanofarad. And I added one extra resistor here to make the oscillation more stable. Not so much more to tell about this circuit. It's in fact very simple. I do not publish, say, push-pull transistor circuits on my YouTube channel, but anyway, there are many push-pull transistor circuits that are using the same principle to generate a high voltage, but it's always very cumbersome how the output waveform looks like. And I want to refer to the earlier video where I was talking about the wild oscillation, the wild waveform here. So that means that such say the usability of such a circuit is limited only to make a high DC voltage, by the way, afterwards, when you have used here a diode. And the best thing is, of course, to use a real high voltage diode. You can find them in printers. Often in printers there is a high voltage unit that has to charge, say, the powder that is spread over the paper, etc., etc. I don't want to get too much in detail. Much more information is on the World Wide Web. So let's look how this circuit works. Switch on the power supply now. Switch on the scope. And let's see what happens. Always interesting, of course. So, interesting to see, of course. You have here a quite good waveform, kind of block wave. Circuit oscillates on approximately 868 Hertz. But of course, when you change the value of the potentiometer, could be, and that's a kind of pain, could be that sometimes the oscillation stops. So now it is 872 Hertz, say approximately 1 kilohertz, not completely right, but anyway. Let me try to change here the potentiometer here. And that is this potentiometer in the circuit, this one. And by the way, very important when you want to use such a transformer that was made originally for 50 Hertz or 60 Hertz, the frequency must be lower to get a good high voltage out. So that's a reason why I used here a 0.47 microfarad capacitor. It's all experimental, but it's usable, etc., etc. So changing here that potentiometer 47K will have many effects at first. Let me show it. Oscillation stops. I turn that potentiometer back again. So on a certain moment it has to start again. There is a critical, say, piece on the carbon layer of that potentiometer where it oscillates properly. And now it suddenly oscillates on 1.2 kilohertz. Anyway, the waveform is quite good, I think, compared to my earlier video where I have showed many wild waveforms. Anyway, turning the potentiometer again, let's see. Tiny changes in that potentiometer value. Frequency goes down, frequency goes up. There's everything to do. Now the oscillation stops. There's everything to do, of course, with the frequency. And the ideal frequency to make this 50 Hertz 230 volt transformer work. You can surely see now that there's high voltage here. So, important to tell, I soldered in, when you compare it to the earlier circuit, a 120k resistor here. So, I want to show the schematic again. And this 120k resistor biases the second transistor much better. That means that it oscillates more easy on lower and low voltages, say between approximately 6 volts and approximately 14 volts. So this resistor here is key for, say, the somewhat better oscillation in when you want to use this high voltage transformer. Anyway, more or less all to tell. Say, and of course this capacitor plays a role to drop the frequency down to a certain frequency where the resonance of such a transformer is ideal, and when the transformer gets to its natural resonance, that is, in case of a 50 Hertz transformer, often 50 Hertz, but they also have a better resonance, so better performance in terms of changing energy from the primary to the secondary. It often works better on 300 Hertz, and these small transformers, no big transformers by the way, can also transfer more energy in the 300 Hertz up to approximately 800 Hertz range. Anyway, so the waveform again, the frequency again, and when you want to do these experiments, it's always very important to say, when you want to find the high voltage on the secondary side, use a neon tube, small neon tube. Often they are, say, mounted into screwdrivers. You can also use this here, this is a, say, a spare lamp tube. All electronics are removed, only, say, the TL tube here is used, and when you connect it to such a transformer here, this one to that one, could be that the tube lights up, and in such a case you know that you have a good high voltage on AC. Well, that is more or less all to tell. Thanks for watching. By the way, talking about the AC out of such a circuit, I only have 2 minutes, but want to do my best. Talking about the AC out, you can rectify it here with the help of one diode. Could be that you need a typical high voltage diode, because 1000 volt diodes don't have always the same impedance in such a circuit working on, say, 1 kilohertz or 20 kilohertz, etc, etc. I have to stop now. Sorry. That was all.